We see spiral galaxies like this to the extreme limits of the universe. They all basically have the same structure. Within an outer halo, clusters of stars scattered in all directions, a central disk, and a dense concentration of matter in the nuclear bulge at the center. Do we live in a galaxy like this? The problem is that from our perspective in the outer suburbs, tiny dust particles in the disk restrict our vision of the stars, rather like fog in a city. That's why our galaxy appears to be full of dark holes when we view it in visible light. In this program, we shall travel to the very center, with astronomers who use every available wavelength right across the spectrum, from radio waves through infrared to X-rays, to probe the complex mix of gas, dust, and stars that make up our galaxy, the Milky Way. In 1957, when the Russians launched Sputnik 1, the first artificial satellite, the Jodrell Bank radio telescope was there to track it. But its prime purpose was to pick up faint radio signals from astronomical sources. Even today, it remains as one of the world's most powerful radio telescopes, and it has played a crucial part in probing the Milky Way.
The radio signals from space are extremely weak. So in order to collect as much energy as possible, we use giant reflecting telescopes like this one, the 76-meter Lovell telescope at Jodrell Bank. The painted metal surface is made out of hundreds of panels in the shape of a paraboloid. That means the signals come down from space and are reflected from the surface to the focus high above me. Because the wavelengths we use in radio astronomy are about 20 centimeters, the surface accuracy need only be of order a few millimeters. It's hard to comprehend how weak the signals are from space. In fact, if we turned this giant dish on the strongest source in the sky and waited for 30,000 years, we'd still only collect about the same amount of energy as this torch emits in 1 second. This dish has been here since 1957. It's hard to build bigger ones than this, so in recent years, the increases in our ability to look at these very faint radio signals from space has come not from the dish itself, but in the amazing advances in technology in the receivers, high in the focus, up there. At the focus itself is a corrugated feed horn, which channels the radio signals to a low-noise amplifier. It looks like precision plumbing, and indeed it is, but the key element is a tiny transistor deep inside, cooled by a helium gas refrigerator to within 14 degrees of absolute zero.
The development of low-noise microwave amplifiers like these has been crucial for radio astronomers, effectively doubling the diameter of each telescope. And computer-aided design of telescopes like this 32-meter dish at Cambridge have given it significantly greater collection efficiency and at the same time much better rejection of spurious, unwanted radiation from the ground and the telescope itself. Put these two advances together and you can see even fainter sources. The 100-meter telescope at Effelsberg in Germany and the 64-meter telescope at Parkes in Australia, together with the 76-meter Lovell telescope, can between them scan the whole sky, north and south. The colors in this all-sky survey show the relative brightness of radio waves emitted from electrons spiraling along lines of magnetic force at a wavelength of 73 centimeters. The central disk of the galaxy dominates the picture. It's only a map in the sense that it shows brightness in different directions, but gives us no idea of depth. For example, this large loop could be small and nearby, or distant and huge. In 1944, a solution to this depth problem was ready and waiting.
When I was a student, I was asked to review what could be done in the future with radio astronomy, which was then in its very first stage. And I knew that hydrogen was the most abundant atom, and there should be plenty of hydrogen atoms in the galaxy between the stars. And I was looking particularly for a line, and there was one in the ground state where the magnets of the electron and the proton switch, and that gives a line which is very long, 21 centimeters. Unfortunately, nobody had yet made a receiver that was sensitive enough at that wavelength. We had to wait for 7 long years before it ever could be detected. And at that time I was teaching at Harvard. And one day Doc Ewan came into my office, unrolled a long pen recording on the floor, and looking along it I could see the wiggle. There was the line. And 2 months later we also had it in Holland, and that line has been a fruitful source of information on our galaxy and other galaxies ever since.
Every hydrogen atom in our galaxy will give out radiation at this frequency, but we receive it at a slightly different frequency, shifted by its motion, the Doppler effect. So every cloud will appear to shine at its own characteristic frequency, depending on its relative velocity to us. It will be detected at different wavelengths in the spectrum. With this technique, we can measure rotation of entire galaxies. The red-shifted hydrogen on the left is moving away from us, and the blue-shifted hydrogen on the right towards us. The whole galaxy must be slightly inclined to our line of sight. We would detect no difference if it were face-on to us.
This is a typical spectrum, and we can see that the hydrogen line is showing up with emission peaks at many different velocities. For example, this small one here has a radial velocity of minus 100 kilometers a second. That means that its component of motion towards us is 100 kilometers per second because of the differential rotation of the galaxy. And we can see many different peaks, each with their own corresponding radial velocity. Now imagine taking many such scans right along the plane of the galaxy. We plot those results in this plot here, which we call a longitude velocity diagram. And here the longitude runs from 90 degrees past the galactic center at 0 longitude out on the other side to 270 degrees longitude. And along the bottom, the other coordinate is the radial velocity. Our previous scan would show up as just one single slice through this map at a particular longitude, where the different peaks show up with their characteristic intensities at their characteristic radial velocities. But with the panorama of many lines, we can now start to see the large-scale structure due to the rotation of the galaxy. So let's look at the overall symmetry of the diagram about the galactic center here at 0 longitude and velocity. This material here is in the inner part of the galaxy. It's rapidly rotating and moving away from us at radial velocities of 100 kilometers a second. This material over here is in the corresponding distance on the other side of the galactic center, and that's coming towards us at a similar radial velocity.
So the velocity is giving depth information. This long spiral arm is picked out by its velocity, just as Professor van der Hulst foresaw half a century ago. But it's proved very difficult to build up a map. Here's the result so far. Vague hints of arms like a child's sketch. Even so, magnetic field directions seem to line up with them. Just a brief suggestion of the splendid alignment we see in other galaxies, like M83. But the most remarkable evidence that the Milky Way looks like this comes not from the arms, but simply from the rotation speed of the entire galaxy. radio astronomers have tracked the motion of hydrogen well beyond the stars.
For example, in this group of galaxies, you'll see that the optical emission is confined to the small bright bits, whereas the radio emission covers an enormous range, many times the optical extent of the galaxies. What we find is really quite astonishing. If we measure the rotation velocities for galaxies, for all different types of galaxies, we find that instead of falling away, these rotation velocities remain flat. They continue at essentially the same velocity to very large distances. And what this means is that the mass of the galaxy is continuing to increase to very great distances, even though there is apparently no visible matter there. In fact, we know from these type of measurements that most of the mass of the galaxies must be some kind of dark matter. We simply don't know what this dark matter is.
To investigate the influence of dark matter in more detail, astronomers in Leiden have used this 50-year-old telescope fitted with state-of-the-art receivers to make even finer slices in the velocity diagram. Superimposed on a globe, with the Sun at its center, each picture is a snapshot of clouds of hydrogen in our galaxy, moving at decreasing velocity towards us. It's difficult to imagine how much data this involves.
This picture is constructed from 250,000 individual observations. Just as many as I have pieces of paper in this box. Now imagine each one of these pieces of paper containing 1,024 different values, being the different velocities. Then you can get an idea of how much data is actually in this survey.
This record can serve as a scale model for our galaxy. The gaseous disk is represented by the record itself. The Sun is located about halfway in from the outskirts of the galaxy to the galactic center. There's a bulge of stars in the galactic center. The stellar disk extends out to about here, somewhere beyond the Sun. One of the most interesting things about our galaxy is, at least interior to the Sun's location, how thin it is, thin and flat. About as flat as this record is, except in the outer parts. In the outer parts, the galaxy is warped very strongly and becomes much thicker. We've been trying to study this in much more detail. What has been necessary is a new collection of data which samples the velocities, in other words, the distances, in much more detail than has hitherto been possible. Projected onto a globe, the distribution of hydrogen in our galaxy looks something like this. To look at the warp, a good way to do it is to take two slices through the galaxy at different latitudes. You look 5 degrees above the galactic equator and 5 degrees below. Plot the material then in longitude velocity maps, scanning at +5 degrees and scanning at -5 degrees. If our galaxy was flat and you subtracted these two maps from each other, you would just get a black screen. Any systematic deviations are going to show up as differences in color. This subtraction was made, and you can see that there's systematic patterns that are blue as you go on one side of the galaxy and are red as the warp dips below the galactic equator.
Computer modeling suggests that this warp could be a permanent feature. But high above the galactic plane, there are clouds of neutral hydrogen moving quite independently.
If we look at the most extreme velocities, we see the phenomena of high-velocity clouds. These have been known from some time, although we still don't know how far away they are. They're probably somewhere on the very outskirts of our galaxy. In the new data, we can scan through these features in velocity to lower velocities and can establish connections with the lower velocity material residing in our galactic disk itself. You also can measure from a map like this the thickness of the gas layer. The thickness is larger than what would be expected if the gas layer was confined by the stars. The stars, at least interior to the Sun's location in the galaxy, lie in a very thin disk, and the gas layer confined by them lies likewise in a very thin disk. In these outer parts, where the stars are very scarce, it's the dark matter which is determining the thickness of the disk. The dark matter obviously resides in a much wider distribution because the gas layer shows a much wider distribution in latitude. If we look at another velocity slice, at a velocity closer to zero velocity, corresponding to the motion of the sun around the center of the galaxy, we're looking at material which is much closer to us. So we can see it in much more detail. The amount of detail is remarkable. We see filamentary structure. We see what look like shells and bubbles, sometimes associated with supernova remnants. We see very wispy structure. These structures have very characteristic velocities. The interstellar medium looks like it's boiling. These remarkable gaseous filaments bear a lot of resemblance to what is being observed in the dust. But the dust observations require infrared techniques.
In the early 90s, Derby, the diffuse background experiment on NASA's Cosmic Explorer satellite, opened new windows on our galaxy at 10 wavelengths all across the infrared spectrum. At the shortest infrared wavelengths, corresponding to the hottest sources, the radiation comes mainly from stars. They clearly outline the central bulge of the disk, with lots of nearby bright stars filling the sky. But as we switch the camera to longer wavelengths, the picture changes dramatically. The bright thin disk along the galactic plane is still there, but the central bulge of hot stars has almost gone. However, right across the sky is a fuzzy S-shaped band of light called zodiacal light. It comes from very close by, interplanetary dust heated by the sun in our own solar system. At even longer wavelengths, this re-radiation from warm dust becomes even more prominent. But now we can see intense radiation from interstellar material concentrated along the galactic plane and extending well beyond the nuclear bulge. And just below the plane, the camera has detected radiation from the distant Magellanic Clouds, our nearest galactic neighbors. At the very longest wavelengths, we are looking at cold interstellar dust. Wispy traces seem to fill our view of the entire sky, with no identifiable features. All very pretty, but what do these images tell us about the shape of the Milky Way? For instance, is there evidence for a bar-type feature in the center of our galaxy, as in this one? This might be an indication of how our Milky Way has evolved. In this picture, all the data have been combined to remove the effect of dust and show directly the distribution of the stars near the central bulge. The brightness has been color-coded from white through red down to green and blue for the faintest stars.
The question now is, can we see evidence in the shape of this light distribution for a bar-like feature in the Milky Way? When we look carefully now at this 1 micron map, we see that indeed it is a little bit fatter looking to the left of center than to the right, and it is indeed a bit brighter at each point to the left of center than the corresponding point to the right of the image. So the Derby data, giving us a multi-wavelength view of the central bulge of stars in the galaxy, is supporting the idea that the Milky Way might indeed be a barred spiral galaxy.
Radio observations also show evidence for the existence of a bar in the central parts of our galaxy. If the orbits of the gas were circular, then there would be a sharp transition as the line of sight crossed longitude 0 between positive velocities and negative velocities. In fact, the observations both of neutral hydrogen and of carbon monoxide show a blurring in this transition across longitude 0. This blurring is consistent with motions along elliptical orbits associated with a bar. Moving from the length scale of the bar, we find a region which is a unique laboratory, where phenomena occur which occur nowhere else in the galaxy, right down in the center.
In this impressive radio image of the central few hundred light-years, we can see dramatic evidence of streams of ionized gas moving rapidly along strong, arching magnetic fields. As we approach even closer, we see wispy filamentary shapes in the central few light-years, curving away from a bright radio source. And at the highest resolution, astronomers have identified Sagittarius A star as the compact source at the very center. To see if there are stars behind these whirling curtains of dust and plasma, astronomers must look in the infrared wavelengths. They have developed large-scale supersensitive arrays of infrared detectors that can produce images like this. The atmosphere makes the picture jiggle around, but astronomers at Garching's Max Planck Institute program their computer to realign them. After further processing, they reveal hidden stars with increasing resolution.
Now, when I first saw this picture, I was really astounded by the great detail. You could see, obviously, single objects, single stars in there. And when looking at different colors, different wavelengths in the infrared, we can actually now see that these individual stars have individual colors, infrared temperatures. And from this, for instance, in the very center, we see there's some blue objects there. Obviously, hot stars. They must also be very luminous. What kind of stars are they? For this, we need to do more than just imaging. We need to use spectroscopy. And it turns out in these blue objects, there is very strong line emission coming from the surface of the star. And these lines you see here have a great width of about 2,000 kilometers per second. So that means that there is gas which is coming off those stars at great speed. So these stars are losing mass. Such stars are known elsewhere in the galaxy to be very powerful stars in the late stages of their evolution, and they cannot be very old. They can only be about 1 or a few million years old. So how have these stars formed? That's a very difficult question, because normally we think that stars form out of interstellar material, and we can look at the interstellar material in the galactic center. And for instance, in this picture you see again the radio image in contours, and surrounding it in false color is the distribution of a poisonous molecule, HCN, hydrogen cyanide, which we use to trace the dense interstellar material surrounding the galactic center. Now, there is obviously a ring-like structure swirling around the galactic center, and while that's interesting by itself, you also see that in the very central region where the stars and the ionized gas is, there doesn't appear to be very much material. So how can stars form if there is not very much material? And there, the fact that the stars in these high-resolution pictures are so closely crowded may help. Stars may collide and merge and then form massive stars. There also appears to be a wind coming from the radio source. What we see here is the radio emission you've seen before in grayscale. And on top of that, in color, you see the emission of an ion emission line in the near infrared. Now, the radio point source is this red blob in the very center. And that's where we see this beautiful bow-shaped structure, which indicates how this wind interacts with its environment. Now, what could Sagittarius A star, the radio point source, actually be? Now, the most plausible explanation probably is that it is, in fact, the very center and a very massive central black hole. To really find out whether or not there, in fact, is a black hole in the galactic center, we need to measure closer in. And in fact, I think in the next few years we can do this with a very high-resolution techniques and determine whether or not there is a black hole at the center of our galaxy.